Okay, let's talk about Chapter 28, the evolution and distribution of galaxies in the universe. So we'll talk about observation of distant galaxies, mergers, distribution of galaxies in space, dark matter, and the formation and evolution of galaxies and structure in the universe. So this is cool. This is a galaxy cluster, a cluster of galaxies. You can see all the different galaxies in this picture. Yeah, it took 70 orbits of the Hubble Space Telescope to take in enough light for this image of this galaxy cluster. And there's hundreds of galaxies here, and this galaxy is 3.5 billion light years away, which means the light is 3.5 billion years old when it left and was on its way to us. There's a cool thing, some gravitational lensing here because of this, which allows us to see 3,000 distant galaxies being warped around this galaxy cluster, which is cool. These galaxies appear blue because of they're younger, right after the Big Bang, and so they're producing lots of hot blue bright stars. So anyway, so all this is just talking about as we go further into space, as we look further out into space, we see galaxies as they were younger and sooner after the Big Bang. And the first generation of the stars, remember, they don't have many heavy elements in them. So we think of the Milky Way itself having been born at least 13 billion years ago. And our best guess of the age of the universe is about 13.7 or 13.8 billion years old. And so all of these things lead to that number. There's a bunch of different things that try to get us there. This is a very far away galaxy. It's 13.2 billion light years away, which means it's one of the youngest galaxies in our universe that we've been able to see. So this is pretty cool. Let's continue through this. Yeah, this is a really great image. This is the Hubble Ultra Deep Field image. That's the result of an 11-day long observation with the Hubble Space Telescope, about a grain of sand held at arm's length. It was a pitch black area of the sky, and when they took the picture, this is what came back, and it kind of blew everyone's mind. Basically, a picture filled with galaxies. Just unbelievable. So there's a bunch here, all with their redshifts, showing them to be quite old and quite distant. So shapes are different. Redshifts correspond to galaxies with similar sizes and similar masses. So we sort of see the evolution of the universe in this image by looking at them as a function of their distance and time. And there you go, one of the furthest, faintest, smallest galaxies ever seen. Just unbelievable. Okay, so what is this? New. There we go. Okay, so galaxy mergers and active galactic nuclei. So the idea here is galaxies grow. Our best guess now is that they merge from smaller galaxies, merge into bigger galaxies. And so there's a bunch of pictures of mergers here, galaxies merging together. This is a wild one. Look at this galaxy there and galaxy here, and this one's just smashing into it. Yeah, so anyway, we see a lot of galaxies colliding today. There's a simulation of some mergers. Yeah, this is pretty cool. So our best guess today, so the Hubble Deep Field images and the images of galaxies as we look further out into space show us at the same distance from us, galaxies look roughly the same. And as we get closer and closer and closer to us, galaxies get bigger and bigger and bigger, and they get more red, more yellow, as there's less, actually there's more older stars as the galaxies develop. And so we are able to study that evolution. So that's your main takeaway here. And here's a wonderful thing. Stephen's quintet here, 5 galaxies all interacting. You can see the 1, 2, 3, 4, 5 galaxies all merging together. Just a wonderful image. Pretty cool. And here you go, some more. This is 8 billion light years away. These are a galaxy cluster really far away, and you can see the merging happening in these really far away distant regions. So again, we can study the evolution of the universe by looking at these galaxies. That's pretty cool right there. Okay, so the distribution of galaxies here. The cosmological principle says that the universe is both, sorry, I'm yawning, isotropic and homogeneous. Okay, so make sure we understand what that means. So the cosmological principle says that since the universe is isotropic and homogeneous, then by studying it where we are here tells us about what the rest of the galaxy and the rest of the universe is. It gives us the ability to study the universe. If that principle doesn't uphold, then we can't really learn about the universe at all. We can only learn about our local area. Speaking of our local area, the local group is the local group of galaxies. It's the Andromeda Galaxy, Triangulum Galaxy, and the Milky Way Galaxy, plus a bunch of other dwarf galaxies. And so this is our local group here. You can see Andromeda is right. Andromeda is right there. Milky Way is here. Triangulum is, look for Triangulum. I think we just have Andromeda in this image, maybe. I can't see it. Okay. Maybe it's, yeah, I can't see it. So that's our local group. So you see there's a bunch of irregular galaxies like IC 5152. But there's a lot of elliptical ones, which are older, larger, redder galaxies. And then the two spiral ones, Andromeda and Milky Way Galaxy. Oh, there's M33. Okay. And so that's our sort of local group there. That's a pretty cool diagram there. Okay, the Virgo cluster then. So our local group is part of what's called the Virgo cluster. And the Virgo cluster is a very large area. It contains a bunch of galaxies, including Galaxy M87, which is where the black hole is, the Event Horizon Telescope took a picture of. So this is pretty amazing, pretty cool. Coma cluster, another cluster of galaxies. So galaxy clusters can lens gravity. So when you have enough gravity here from one galaxy, 2 galaxies, 10 galaxies, then you can get this gravitational lensing effect. And it's because, again, light falls. So light coming this way is going to be bent, fall towards the galaxy, come towards us, which means it's going to appear to come from this direction because of that rotation. Okay, so that's a great example of those 4 points because of gravitational lensing. So that's a quasar that's back here behind this, but the light from it, as it radiates out, some of it gets bent as it comes around this galaxy, and it ends up making these 4 points of light. Great example of gravitational lensing. Here's another wonderful image. Look at the warping there. Look at how smeared out that is. And same thing, this galaxy just appears to be way smeared out because of gravitational lensing. All right, so superclusters are these massive areas of gravitationally linked galaxies, and this is the Sloan Digital Sky Survey. This is getting the redshift of all the galaxies. We can't see anything in this region here because that's the plane of the Milky Way galaxy, so all the gas and dust blocks our view from there. But you can see every one of these colorful points is the redshift of all these galaxies. And so the redshift is basically the how far away it is too, because Hubble's law found a link between the redshift and the distance and the recession velocity. And what you can see here is all these close galaxies have kind of a green color. The further away you get, the more red color there is. And you can see that the galaxies, they live on sort of this web, and I can trace out the galaxies here as being on these kind of filaments and voids, we call them. So the blue line there would be the filament, and then this in between the blue lines are voids. and the voids are just empty spaces. So that's what you're looking at here. Let me look at these voids, 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 void, 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 void. So the way we think about this is soap bubbles. It looks like the universe was bubbly and galaxies formed on the bubbles, but didn't form in the voids. So your filaments and your sheets are where all the superclusters are, and then the voids are spaces where there's nothing. Let's see. Yeah, Sloan-Digital Sky Survey is a really cool instrument, and they had these plates where they knew the locations of galaxies, so they put these optical fibers where when they pointed the telescope at a region of space, the galaxy's light would land directly on those fiber optics, and then those fiber optics were put into spectrometers so that they could measure the redshift of the thing, which is, they're pretty cool plates. Yada, yada, yada. Okay, so then dark matter. So we talked about dark matter. The further away you go from a galaxy, you'd expect that the stars would be going really fast here and then slow down as you get further out. Well, we find sort of the opposite, that the speed is actually increasing the further you get away from the center of the galaxy. We'd expect it to slow down, but what happens is it kind of speeds up there. So the further away you are from the center of the galaxy, the faster the stars orbit. The only way to explain that is with extra matter, which is pulling on those stars with enough force. And it turns out that the radius of the dark matter halo is maybe 3 times larger than the galaxy itself that we think of. So our galaxy might be this big, but the dark matter halo might be, that big. Okay, so we also see that there's dark matter in galaxy clusters because of the gravitational lensing effect. You can see in here there's some lensing. There's lensing everywhere because of the mass of the galaxy cluster. And so based on that lensing, we also find that there's more matter than we'd expect there. And then also, this is a very famous image that shows X-rays, and we try to compare the amount of matter coming from here with the visible light to estimate the mass. And what we find is that most of the mass is in the form of dark matter because we can't see it, which is pretty crazy. So here's your mass to light ratio again. To compare the amount of mass to the amount of light, to find a comparison to the number of stars and the number of mass based on the brightness of it. So is most of the mass in a dark form, or is most of the mass in a light form, basically? What we find is that there's dark matter. So we don't know what dark matter is. We assume it's a particle. There's 2 ways to think of dark matter, and one is with machos and the other is with WIMPs. Machos stand for massive compact halo objects. So in other words, maybe our galaxy is filled with brown dwarfs and black holes. So for example, go back to the dark matter curve here. Out here, far away from the center of the galaxy, well, maybe there's just a ton of black holes out there, and we just can't see them. It's possible. Maybe there's just a ton of brown dwarfs we're not keeping track of. Maybe there's a bunch of, all these things that are super massive, but they got to be very compact. So that's why we call them massive, but also compact halo objects. So it's not that, we don't think. Could be very, very small black holes. We haven't ruled them out completely. We call them primordial black holes, but we're still trying to figure that out. The other thing we're looking for is called WIMPs, which are called weakly interacting massive particles, WIMPs. And I don't see WIMPs here, but the 2 types of WIMPs are hot or cold. So it just has to do with particles that, like neutrinos, they travel at close to the speed of light, or cold, that are more like, bowling balls or something, and just kind of sit around there and don't move but have a lot of mass. So we're trying to figure out what what they are. We're leaning towards cold dark matter, a particle that moves slowly and can hang around for a while. So we don't know what that is yet, but we're looking. Another thing is this stuff called dark energy, which we'll talk about when we talk about cosmology, but that's a different story. And that's basically what's driving the expansion of the universe. Okay, formation, evolution of galaxies and the structure in the universe. So galaxies form and grow from gravity pulling in and heating them up, and so you have this cloud of hydrogen. It collapses down into a disk. As that forms, you get basically the same process happening on a smaller scale. So you get little stars forming. You get another smaller galaxy kind of colliding and forming and being merged into it, and you just end up with growing and growing and growing galaxies. The formation of superclusters and voids. It's actually really interesting because in order to start the seeds of the collapse here, this primordial hydrogen cloud, to form the galaxies, we actually need the dark matter to coalesce first. So let's see if we talk about this here. So basically you've got these smaller clouds of gas, and as they contract together, they form your galaxies, and then you get your clusters of galaxies, and then those form together to form your super galaxies. But it actually turns out that in order to get the structure that we see, where there's filaments and voids from the Big Bang to the present, we actually need dark matter to do the collapsing first. So the dark matter forms clumps first, and then the visible or luminous matter is attracted to those dark matter clumps, and that is what gives us the structure that we see today. Okay, so what do you need to know about? We use Hubble. We can look far into the past with our telescopes and see that the universe is about 13.8 billion years old. And the furthest things we can see are about 13.2, 13.3 billion light years in terms of galaxies. So that gives sort of a limit on the formation of galaxies from the beginning of the universe. And then we know that they merge from bottom up, and the distribution of galaxies in space are homogeneous and isotropic. Leads to the cosmological principle. The challenge of dark matter is that we need dark matter to form galaxies. It has to form first. It explains the rotations of stars. It explains the rate that galaxies are formed. It explains why our universe is 13.8 billion years old. If we didn't have dark matter, a lot of the galaxies would have burned out by now because they would have collapsed a lot sooner. And just, it would have been wild. But we don't know what it is. Could be machos, could be wimps. We're still trying to figure that out. The reason we don't know is because we don't have data. So there's a ton of ideas, a ton of great ideas, a ton of explanations that work, but we don't have direct evidence that backs up any of our ideas, and we're currently conducting a bunch of experiments to figure that out. Formation of evolution of galaxies and structure in the universe. We need this dark matter to form, and then our galaxies to form, and then they build up into these larger groups over time. Okay, talk to you later. Bye.